In this video, we are going to talk about algebraic properties of R. We will discuss the field axioms of real numbers, and then we will prove some important algebraic properties of real numbers derived from these field axioms. So if you're ready, let's start. Throughout the course of real analysis, we will focus our attention to the set of real numbers. This set of real numbers are composed of the set of natural numbers, set of rationals, and set of irrationals. To recall, the set of counting numbers are composed of the numbers 1, 2, 3, and so on. So this set is denoted by the blackboard letter N. Now, together with the negatives of these natural numbers, negative 1, negative 2, negative 3, and so on, and the number 0, so we form the set of integers. So, the set of integers is denoted by blackboard letter Z. Now, if we divide two integers, except when the denominator is 0, what we get is a fraction or a quotient. For example, 1 divided by 2, or 2 divided by 3, or negative 1 over 4. Or sometimes you can also express this quotient as decimals. So for example, negative 0.1. Now, there are also fractions which when we express as decimals, we get what we call a non-terminating decimals. But for rational numbers, when the decimal is non-terminating, it's always the case that the digits are repeating. For instance, when we have the rational number 2/3 in decimal, it's represented by the number 0.666 and so on. So the digit 6 repeat indefinitely. So all these numbers, we call the set of rational numbers. And we denote this set by the blackboard letter Q. Now, there are also numbers whose decimal representation are non-repeating and non-terminating. So, for example, we have the number pi with representation 3.14159 and so on. So, the digits of the number pi will not terminate and the digits will not repeat as well. So these numbers that are represented or whose decimal representations are non-terminating and non-repeating are called irrational numbers. So the irrational numbers is represented by the blackboard letter Q prime. So the prime denote that in set theory, this is the complement of the rational number. So we call it the irrational number. So other irrational numbers are the Euler number E, or approximately 2.71825. But of course, these digits will not terminate. We also have square root of non-perfect square numbers like square root of 2. So that's approximately 1.414. Or the logarithm of 2, that's 0.30102 and so on. Or any decimal number, or as long as the digits does not terminate and does not repeat, then that's an irrational number. So no irrational number is irrational number. And no rational number is irrational. So together, the two of them form the set of real numbers. So the set of real numbers is denoted by the blackboard letter R. Now, the set of real numbers under this two binary operation constitute what we call a field, and this field satisfy the following axioms. Commutative property of addition, which we will call A1. For any real number A and B, we have A plus B is equal to B plus A. Second property A2, associative property of addition. For any real numbers a, b, and c, we have a plus b quantity plus c is equal to a plus the quantity b plus c. The third property, A3, existence of additive identity. In the set of real numbers, there exists a number which we call 0 that satisfy the following condition. For every real number a, we always have a plus 0 or 0 plus a is equal to a. The fourth property, existence of additive inverse. For any real number a, you can always find another real number which we will denote by negative a, such that the two numbers satisfy the following condition. A plus the negative of a, or we can have negative of a plus a is equal to the additive identity 0. This negative of a is called the additive inverse of a. A2, A3, and A4 are actually the three conditions for the set of real numbers to be considered as a group. Since this is an abstract algebra concept, all properties of the group discussed in abstract algebra also holds in the set of real numbers. Together with the first property, commutative property of addition, then we say that the set of real number under addition is actually an abelian group. Now, let's go to the second operation, multiplication. We also have four property of multiplication. The first property under multiplication, M1, commutative property of multiplication. So basically, it's the same as any other commutative property. If you have two real number a, b, then whenever you have a times b, that's equal to b times a. For the second property, M2, associative property of multiplication, whenever you have three real numbers, a, b, and c, a times b quantity times c is equal to a times the quantity b times c. The third property, existence of multiplicative identity, which we will call M3, state that in the set of real number, there exists a real number which we will call 1 such that it satisfies the following condition. For any real number, we always have a times 1 is equal to 1 times a is equal to the value of a. 1 here is called the multiplicative identity. So any number, if you multiply it by 1, the result is the same number. And for the fourth property, existence of multiplicative inverse, or M4, so for any real number except the number 0, we can always find what we call a multiplicative inverse. So we will denote the multiplicative inverse as a to the negative 1, or simply call it the reciprocal of a, or the multiplicative inverse. So for any real number a except the number 0, we can always find a real number a inverse such that the two numbers a and a inverse satisfy this condition. A times a inverse is the same as a inverse times a, and that's equal to the multiplicative identity 1. Basically, these four properties here tells us that the set of real numbers also can be considered as an abelian group under the multiplication operation. Now, for the last property of the field axiom, we add another property, distributive property of multiplication over addition, or sometimes we'll just call it D, or DPMA. The distributive property of multiplication over addition gives us a rule whenever we are multiplying a sum. So suppose we have three real numbers A, B, and C, and that we have the product of A and the sum of B plus C. So DPMA states that this value is equal to A times B. So we are now distributing A over B plus distributing A over C. So we are distributing A to B and to C. So we have A times B plus A times C. If we have a sum times another number, so we can also distribute A the same way. So we have B times A plus C times A. These 9 properties are what we call the field axioms of the set of real numbers. Again, remember that these field axioms are the same as the group properties, which was discussed in your abstract algebra course. So any property derived or discussed in abstract algebra course holds true in the set of real number under the operation addition and multiplication. So now let's prove some properties derived from this field axiom. Let's prove that the identity element 0 is unique. So if we have two real numbers A and C such that C plus A is equal to A, then C is equal to 0. Okay, so let's prove that. So what we want to show is that C is equal to 0. Whenever you want to show equality, all you need to do is to start with the left-hand side. And by using the field axioms, appropriate field axioms, we must be able to show that the left-hand side is equal to the right-hand side. So let's start with C. Now, what we can do is we can use the field axioms to find equivalent statement for C. We know that by the existence of additive identity, C is the same as C plus 0. So that's the existence of additive identity A3. Now, since we have another real number A, by the existence of additive inverse, we can get the additive inverse of A and then add it with A, and the result will be 0. So we have C plus, we can replace 0 by the value A plus the negative of A. So again, that's from the existence of additive inverse. So we have C plus the quantity A plus negative A. So whenever we have three real numbers, we can regroup them by the associative property of addition. So this can be written as C plus A quantity plus the negative of A. So we regroup C and A together. Again, that's from associative property of addition. Now, using the given, we have C plus A is equal to A. So we will just substitute the value A for C plus A. And then we will rewrite negative A. So that's the given or the hypothesis. But again, since we have A plus negative A, that's equal to 0 by the existence of additive inverse. So we were able to show that C is equal to 0. So this only means that there is only one value that will not change the value of A. So whenever you add something to A and the result is still A, so we have C plus A, the result is still A, then that value that we add, that value C, is equal to 0. Therefore, 0 is unique. The additive identity is unique. That's called the uniqueness of the additive identity 0. Similarly, we can also show that the multiplicative identity 1 is unique. So if we have two real numbers y and b where b is not equal to 0, such that y times b is equal to b, so you multiply the numbers y to b and the result is the same as b. Then we conclude that y is equal to 1. So again, we want to show the equality y is equal to 1. So we can start with the value y and then we can substitute an equivalent statement. Now, using the properties of multiplication this time, we can see that y is equal to y times 1. That's the existence of multiplicative identity, or we call that M3. Now, from the given, we know that B is not equal to 0. So, any number that is not equal to 0 by the existence of multiplicative identity must have an inverse. So, that means we can rewrite 1 in our equation as B times its inverse, B inverse. That's the existence of multiplicative identity, or M4. Now, we have three real numbers, y, b, and b inverse being multiplied together. So, we can regroup, or we can group together instead of b and b inverse. We can group y and b. So, this is the same as y times b, group them together, times b inverse. Again, that's the associative property of multiplication, or that's what we call M2. Now, from the given, y times b is equal to b. So, we can replace this by b and then copy b inverse from our given. But b times b inverse, as we know from the existence of multiplicative inverse, is equal to 1. So, again, that's M4. So, we were able to show that y is indeed equal to 1. So, that means whenever you have the product y times b equals b, then there can only be one value for y, and that is y equals 1. Meaning, 1 is unique. Okay, here are some special properties of the number 0. Multiplication property of 0. If a is a real number, then a times 0 is equal to 0. Basically, what this tells us is that any number, if you multiply to 0, the result is 0. Now, how do you prove that a times 0 is indeed equal to 0? What we're going to use is the uniqueness of the additive identity of the number 0. Again, if you have a real number z and you add it to any number and the result remains the same, then you can only have one conclusion. That number c must be equal to 0. So, how are we going to use this to show that this value here is equal to 0? To use this property here, what we can do is we can replace c by a times 0, and then we can add that by a, and we need to be able to show, so this is what we want to show, that it is equal to a. Now, if we were able to show that a times 0 plus a is the same as a, then we can make the conclusion that a times 0 must be equal to 0 by the uniqueness of the additive identity. Okay? So, this is what we want to show. We want to show that a times 0 plus a is equal to a. So, we're not showing directly that a times 0 is 0. We are going to show first that a times 0 plus a is equal to a. But by doing so, we can conclude, because of the uniqueness of the additive identity, that this value here that we add to a must be equal to 0. Because there's only one value that when you add to a, the result remains a. Right? When you have c, you add it to a, the result is a. The valid conclusion is that that value here must be 0. So, using that same conclusion, if we have a number a times 0, and we add it to a, and we were able to show that this is equal to a, then the only valid conclusion is that a times 0 must be 0. So, what we want to show is that a times 0 plus a must be equal to a. So, let's start with the left-hand side. So, again, if we want to show an equality, we always start with the left-hand side, and then we show that it is the same as the right-hand side. Now, a times 0 plus a can be written as a times 0 plus a times number 1. Why? Because 1 is the multiplicative identity. So, that's simply M3, existence of multiplicative identity. Now, because we have a common factor here, a, by the distributive property, we can factor that out. So, we can have a times the quantity 0 plus 1. So, again, that's the distributive property of multiplication over addition. Now, looking at the parentheses, we have 0 plus a, but 0 is an additive identity. So, that means we can have simply 0 plus 1 is equal to 1. That's A3. But 1 is the multiplicative identity. So, meaning A times 1 must be equal to A. That's M3. Existence of multiplicative identity. So, what we were able to show is that this value here, A times 0, if you add it to A, the result is also A. So, by the uniqueness of the additive identity, there's no other value for A times 0 but 0. So, we will conclude that A times 0 must be equal to 0 using the uniqueness of the additive identity 0. Another special property of the number 0 is the zero product property. So, let's look at the zero product property. If we have two numbers, A and B, such that their product is 0, there can only be two possible scenarios. Either A is equal to 0 or B is equal to 0. Of course, the logical operator or here means that it can happen that both of them is equal to 0. So, what the property is saying is that if the product is 0, then at least one of the factors, either A or B, is 0. Again, it can happen that both of them is equal to 0. In predicate logic, whenever you want to prove an OR statement, we can use the disjunctive syllogism technique. So, if you have P or Q, and then you show not P, you need to be able to show that it is Q. Again, in logic, P or Q and not P means Q. So, meaning, for the conclusion to be valid, what we can do is we can suppose the negation of P and we will show that Q must be true. So, assume that the negation of P is not true. So, assume that A is not equal to 0. What we want to show is that B is equal to 0. So, this is what we want to show. If we assume that A is not equal to 0. So, again, if we want to show that B is equal to 0, then we can start with B, the left-hand side, and then let's show that it will be equal to 0 on the right-hand side. Using the same technique that we've used a while ago, we can write B as 1 times B. Again, that's by the existence of multiplicative identity, or that's M3. But since A is not equal to 0 by assumption, then it must have an inverse, right? So, meaning, we can rewrite 1 as A inverse times A quantity, and then we copy B. That's the existence of multiplicative inverse. We were able to determine that A must have an A inverse because of the assumption that A is not 0. Now, we can regroup multiplication. That's associative property of multiplication. So, we have A inverse times quantity A times B, or that's M2. But from the given, A times B is equal to 0. So, we can substitute the value A times B equals 0. That's our hypothesis. But for any number, remember our zero multiplication property of 0, property number 1, any number times 0 is 0. Again, that's property number 1. So we were able to show that b is equal to 0. And that completes our proof. There are a lot more other properties of the set of real numbers, which we will no longer discuss here. Again, these properties are the same properties that were derived in abstract algebra. For instance, if we have a plus b is equal to 0, then that means that b is equal to negative a. Meaning, if you add two numbers and the result is 0, then that two numbers are the additive inverse of each other. So the additive inverse is actually unique. Number 2, the additive inverse of the additive inverse of a is a itself. So if you get the additive inverse of a, and then you get the additive inverse of that additive inverse, then you're back to a. Negative 1 times a is the same as the additive inverse of a. So that means if you have negative 1 times negative 1, by this property, that will become the negative of negative 1. But the negative of negative a is a. So that means that the negative of negative 1 is simply 1. Number 4, the additive inverse of a and the additive inverse of b, if you multiply them, that's the same as just multiplying a and b. Number 5, the additive inverse of a plus b is equal to the additive inverse of a plus the additive inverse of b. So that means you can also distribute additive inverse. So these properties, we will no longer discuss how to prove them and will be left as an exercise. So these are good practice to reinforce the knowledge that you learned in our discussion. Recall that in the set of real numbers, we also have two more operations, the difference and the quotient of two real numbers. So for real numbers a and b, the difference of a and b, which we write this way, and that's usually read as a minus b, is defined as the sum of a and the negative of b. So meaning, if you want to get the value a minus b, basically what you're doing is you're getting the sum of a and the negative of b, or the additive inverse of b. That's why this operation is derived from addition and the additive inverse. Now, if b is not 0, then we can also get the quotient of a and b. And usually it is written this way: a over b, or sometimes we also call it divided by. So a divided by b, or a over b. Other way to write this is, instead of using a slash, we use a horizontal bar. So we put on top a and then at the bottom b. So that's a over b. So a over b is defined as the product of a and the reciprocal of b, meaning the multiplicative inverse of b. So we define a over b to be the value a times b inverse. From this representation, we have the following notation. If you have a, that's basically a to the 1. Now, if you have a times a, that's actually equal to a squared. By induction, a cubed can be written as a squared times a, or that's equal to a times a times a. And so on. So in general, if you want to write a to the n, basically what that means is that you have a times raised to n minus 1 times the value of a. Or that's a times a and so on, where you have n factors of a. Now, let's incorporate the inverse symbol. We have 1 over a defined as 1 times a inverse. But since 1 is the multiplicative identity, then this is simply A inverse. Meaning, 1 over A is A inverse. So that if we want to square 1 over A, or that means we have A inverse times A inverse, multiplying A inverse to itself, then that can be written as A inverse squared. Now, following the laws of exponent, this can be written as A to the negative 2. Similarly, if we want to write 1 over A cube, then we can have A inverse cube. Following again the laws of exponent, we have A to the negative 3. And so on. So, 1 over A to the n is the same as A to the negative n. So, we will follow these notations and we will no longer bother discussing the proof. Again, these are just derived from your abstract algebra. So, without proof, we will follow the rules of exponent. We have the following laws of exponent. If we have A times B, and then you raise it to n, then that's the same as A to the n, B to the n. If you have A over B, and then you raise it to n, then that's the same as A to the n over B to the n. If you have A to the m times A to the n, then that's simply A to the m plus n. If you have, on the other hand, A to the m over A to the n, then that's A to the m minus n. If you have A to the m and then this is raised to n, then that's the same as A to the m times n. Again, we will no longer show the proof of the laws of exponent, and this will be left as an exercise.